We had a question about a type of problem that comes up in chapter 12, and here's an example of one of those. So we have a uniform planck. So let's see, there's a typo here. So a uniform planck has a mass 2m, and a bowling ball has a mass m. So here in the picture is the bowling ball and the planck. The length of the planck is 5 meters, and it rests horizontally on 2 supports as shown. So the total length is 5 meters, and then the distance over here is 2 meters. They want to know is what distance x tip, and this distance is measured from here. Can the ball be rolled before the planck starts to tip? So like I said, there's a bunch of these in chapter 12, and so let's go over this one here to try to help you do this. And so this is a equilibrium style problem. All right, so we're going to look at this, and so here's our answer. It comes out to be 1 meter. And so here's our picture. So now if we look at the forces acting on the planck, okay, so here I'm going to call this normal force 1 from the left side. And then right here, I'll call this normal force 2 from the right side. Then there's going to be mg of the bowling ball. And at the center of the planck, the center of mass of the planck, that's just going to be 2 mg. So I'm just going to say because it's got 2 times the mass of the bowling ball. Now, so there's a total of 4 forces, and there's 3 things we don't know. We don't know N1, we don't know N2, we don't know X tip. So the problem is we need an extra piece of information to do this. And the trick is that what happens is, so this ball gets to this position here where it's just about to tip. Okay, so when the bowling ball gets to the position where it's just about to tip, the force of N1 goes to 0. So this is sort of the trick. So in all these problems, one of the forces will be 0. So when planck is just about to tip, N1 is going to equal 0 because the planck's going to tip about N2, and so N1 will have to be 0 at that point. So we make our axis right here. So this is our axis, and so we do our usual torque positive equals the torque negative. And so here, again, N1 would be applying a torque normally, but at the point where it's just about to tip, that N1 will apply no force there. Another way you can think about it is when it's just about ready to tip, I could take this support beam and move it out of the way. All right, and basically all the other forces are balancing, and so it's just about to lift off of there, and that's sort of what's going on here. And so the positive force would be the 2 mg, so it'll be 2 mg, and so it's going to have its moment arm, and the negative force is going to be just the mg times its moment arm. Now in the picture, it's really nice. The moment arm for this one is the thing we're solving for, x tip. And the moment arm in this case would be this distance right here. And so you've got to do some calculating. So we know this is the halfway point. So over here, this is 2.5 is the total length, or 5 is the total length. So 2.5 would be the length from here to where the force 2 mg is acting. So if that's 2.5 and this is 2, then this little distance in here is going to be 0.5 meters. So make sure that that makes sense to you. And that's it. So at the point where this is just about to tip, basically the torque of the 2 mg equals the torque of the mg. And because we're doing it about this axis here, we don't care about any force that N2 is applying. And so what we can do here is just cancel out the mg's, because this again was twice as big. And you see what happens is you get the answer as we thought from before, or as we stated in the answer, is that it's 1 meter.